Yeah, it's going to have to wait, eh? Random variable thing, combining two random variables together, x and y. Okay, so we've done that before, right? You can like take x plus y, x times y, this sort of thing, but I sort of talked more about that. And we're halfway through our important theorems, yeah? Anyway, one of the important theorems about variance is that you don't have to subtract everything individually from the mean and then square it and run over the probability distribution. You can actually take a shortcut and just take the expectation of the square, but you'll have to subtract off the square of the mean as a correction. It's a very, very useful thing to have at our disposal. Okay, so that's one thing about variance. There's another one. Okay, so expectation of variance. Do you have linearity? No, you don't. And it sort of makes sense you don't have linearity. If you multiply by a, you're actually amplifying the square of the difference by the square of a, right? So it shouldn't be linear, but it will be by the square. That sort of makes sense. If you add b on, the b sort of vanishes because, well, you're sliding everything over. You're not actually changing the spread at all. You're just translating things over. And in terms of multivariate, we proved this thing last time as well, that if you take the product of two random variables, and want its expectation, it ends up being the product of its individual expectations, if they're independent. Okay, and if you have several variables, x, y, and z, or w, x, y, and z, whatever, as long as they're mutually independent, this thing scales. Okay, so this thing extends. All right, we have one more thing to do, and then I'm going to introduce you to another concept, and it actually falls out of the proof, as we'll see as we go along. Okay, and the last one is that if you add two variances, add two things, x and y, you take the variance of that, it's actually equal to the sum of the two variances if x and y are independent. Okay, and that's going to turn out to be very useful to us going forward. There's a lot of results that are based on this. Okay, so proof. Okay, start off with the variance of x plus y. We'll do this sort of left-hand side equals right-hand side sort of proof. And from the definition, well, not the definition, but the theorem that I showed you from before, we can just take the square of what's inside and find its expectation and subtract off the square of the variance of that. And as we did before in the previous proof, we're going to use, we're going to expand the thing and we're going to use linearity. We're just going to use them at different times. Okay, so I'm going to start by working with this one term, and I'm going to carry it down a couple steps, and then I'm going to work on this term and carry it down a couple steps. And I hope that's okay with you. Okay, so this one first, we'll expand the bracket, which doesn't take much effort here. That's just x squared plus 2xy plus y squared. Okay, and just to show that we're just working with the first term there and none of the others, we'll just bracket it up and keep it separate. And then we can use linearity on this. Okay, so that's equal to the expectation of x squared plus, well, we'll just do 2 times the expectation of xy plus the expectation of y squared. And we'll pause here for this one to work with this one. This one, we're going to use linearity immediately, and then we're going to expand the bracket. Okay, so the linearity, okay, is going to be expectation of x plus expectation of y. Of course, that's going to be squared. Okay, so that's this bit over here. And then we can expand this bracket. Okay, and I'll just use the red thing right away. Okay, so expectation of x squared plus 2 expectation of x, expectation of y, expectation of y squared. Okay, and essentially we did the same thing to the left bit that we did on the right bit. We just did it in a different order, right? One step we expand the brackets, the other one we use linearity. And I'll give you just a brief moment to catch up. So I'd just like to organize our thoughts a little bit because this is just straight expanding what we started with on the left-hand side. The thing we're looking for on the right-hand side, just a little bit of look ahead, we're looking for the variance of x and the variance of y. Variance of x is expectation of x squared minus expectation of x all squared, and we have those two things here. Seems like we should group them together and try and get this. Same thing for expectation of y and expectation of y squared. Subtract those two, we get variance of y. There's some crap left over, but we'll group that together too. Okay, so what do we get? Okay, just doing a little bit of reorganization. Expectation of x squared minus expectation of x all squared. Okay, so that's two of the pieces here together. That's eventually going to be the variance of x, right? Expectation of y squared minus expectation of y all squared. Again, those two bits together are going to give us variance of y in the next step. There's a little bit of organization, seeing what we have and applying it for what we need. Yeah, there's some crap left over. And what's the crap? Well, I'll factor out the 2. It's 2 expectation of xy minus expectation of x times the expectation of y. Okay, so these things here are kind of nice. We'll just substitute in variance of x and variance of y. That's the stuff that we need. The stuff that's left over we need to deal with. But it's pretty easy to deal with, right? It's equal to 0. Why is it equal to 0? Yeah, good. So the previous page, if x and y are independent, then e x times y is the product of e x and e y, right? So this will give you 0. Now, today, I did not take the big red marker and scratch that thing out, although it was very tempting. The reason that I didn't do that is because this quantity, sort of a byproduct of adding a whole bunch of things together and taking its variance, is a special quantity, okay? So I'm just going to make a note here, rather than scratching out this bit. If it's not independent, this quantity might be 0, it might not be, okay? So this is maybe not 0. Okay, but this quantity has a special name, and it's called the covariance. Okay, so next slide, the covariance is defined to be that quantity. So the covariance of x and y is equal to that difference, okay? The difference between the expected value of x times y and its individual means, okay, taken as product. And there's another version of this, and you can prove that in good time. I think this might actually be one of your assignment problems coming up, so look for it. Okay, some properties of the covariance. First of all, it showed up in that variance proof that we just did. Okay, so in general, even it doesn't matter if x and y are independent. Variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance. Okay, so that thing subs in right there. Okay, so that's good. Another thing, so we saw that. Yeah, so another thing is that covariance is commutative, so you can swap x and y and turn it around, and it doesn't affect things. And sure enough, if you just look at the equation up top here, you're just swapping things around that are commutative by multiplication, so that certainly works. What's the covariance of x with x? It seems a little weird. Yeah, it is. Okay, so if you look at what's happening here, you end up getting, well, let's just try it up here. So this is expectation of x times x, right, which is x squared, minus the expectation of x times the expectation of x, which is the mean squared. That's exactly what the theorem is, right, that snazzy theorem, shortcut theorem to get the variance. Okay, so the covariance of x taken with itself is just the variance. Okay, and the covariance actually indicates how much these things sort of affect each other, in a way. Okay, so if they're independent, clearly we've seen that this thing is 0. But if they're, it's possible that you have a covariance that's positive, and sometimes you have a covariance that's negative. If it's positive, that means that there's like a positive influence between the two variables. So if x increases, y tends to increase. And likewise, if it's a negative value, then if you increase x, it tends to decrease y. That's the effect that it has. Okay, and to show this using some of the techniques that we've had before, we're just going to do a simple conditional probability thing on a binary variable. Okay, just a binary random variable. These indicator variables are 1 if event A occurs or event B recurs, respectively. And if you take the product of x and y, it's also a binary variable. Okay, but it's only going to be 1 if it's 1 times 1, and that's only if both A and B occur, so that's why we use A intersect B. Okay, so it seems to make sense. So what happens if the covariance is greater than 0? Let's have a look. Okay, so the covariance of x and y is equal to the expectation of x and y minus the expectation of x times the expectation of y. And what's the expectation of an indicator variable? This is more of a review than a new thing. What's the expectation of an indicator variable? probability of the event. Yeah. Okay. So the expectation of xy is the probability of A intersect B. The expectation of x is the probability of A, and y, the probability of B. Now, this thing is going to be greater than 0, which means this bit here, the probability of A intersect B is going to be greater than the probability of A times the probability of B. Okay, so they're not independent, okay, but more than that, how they influence it, okay, so the probability that both things occur is greater than the products of, each of them occurring individually. Okay, so if you look at, conditional probability, where you say, okay, the probability of A given B, so if B occurs, what happens to the probability of A? It goes up, okay, and a quick proof of that is by using this, okay, so this is equal to the probability of A intersect B divided by the probability of B. That's just by definition, but the probability of A intersect B is greater than the product of its individual probabilities, right? So that sort of goes into here, right? And those probabilities of B, they go away, and that's equal to the probability of A. So we have the probability of A given B. So B happens, what happens? Well, it's bigger than the probability that A happens just by itself. Okay, so they're both sort of influence each other to happen. And that's the way covariance behaves. And if you wanted it to be less than 0, you would have this thing flipping the other way. So if one thing occurs, it's less likely that the other thing occurs. Okay. Can't hear you, you have to speak up, sorry. It's not an if and only if, yeah, so the question is, if x and y are independent, then the covariance is 0. It's not an if and only if relationship. You can actually come up with variables that are not independent, but their covariance is 0. Yeah, so their covariance is 0 does not imply independence. That's a little dialed in, isn't it? Let's see if we can back that up a little bit. There we go. Cool. Okay, yeah. You don't get why covariance of x and y being 0 means that they're independent. It's not that case. This is if this, then this. It's not an if and only if relationship. So if the covariance is 0, it's not necessarily independent. Yeah. Okay, same. You guys have the same question basically. Yeah. Okay. Next. Correlation. Okay, there's a quantity when you do like data analysis and lines of best fit and this sort of thing, you can compute a number. It's a very easy number to compute. There's a formula for it. It's called the correlation. This is the formula, but there are other ways of doing this as well. Anyway, it's a number between -1 and 1. It's the covariance of the two variables divided by the product of the variances, but to make sure the dimensionality works out, you take the square root on the denominator. Oftentimes you have data sets that are XY scatter plots, and you've done this in science class, and you end up getting line of best fit sort of trend lines, right? So here we sort of see sort of a trend line that looks positive, right? So as x goes up, y goes up. Okay, here's a negative correlation. As x goes up, y goes down, and sometimes there's no relationship at all. Okay, they just fly all over the place. Okay, so this value is an indicator of how tied, okay, how strongly correlated. I mean, so you sort of use the word naturally in English all the time. If you took the correlation of x and x, you would get 1. Okay, now why is that? Well, the covariance of x and x would be the variance of x, and we would have the variance of x times the variance of x. You take the square root of that, you get the variance of x. Okay, same thing for this, except you're going to have -1 as the. Okay, so x should be correlated with itself. As x goes up, x goes up. As x goes up, minus x goes down. I mean, that sort of makes sense. And those are the perfect situations that you can get. I mean, another perfect situation is that they're independent, so you end up getting a correlation of 0 because the covariance will be 0. And the way that it works in terms of trend line, if you do a correlation analysis of the data set, the closer you are to 1, the more correlated the data is. Okay, just as a first approximation. In fact, if you get a number of 1, you can draw a straight line through all of the dots. Okay, so it will fit a linear relationship perfectly. So y is equal to a plus bx, where b is a positive number if the correlation is positive, and it's a negative number if the correlation is negative. Okay, so that's a really nice property to have. Normally, data sets have some noise, some error associated with them, so you won't get exactly 1. But if the number is close, like 0.8, 0.85, something like that, it's very, very well correlated. You say strongly correlated. Something around 0.2, maybe a weak correlation. You don't draw too many conclusions from that. Okay, so always we talk about data sets and try to figure out how the world works, and figuring out how the world works is what we're about at a university, right? So you might try to do data analysis and try to find relationships among things in the real world. I love the book Freakonomics. I read that book. I thought all the case studies were wonderful. If you haven't read it, I highly recommend it. Some of the other things they've written are maybe a little more suspect, but the first book was really solid. Correlation, they talk a lot about correlation and causation because a lot of people refer to these things as the same thing. Okay, so you find some sort of connection among, say, census data, and you say, hey, this is not merely a coincidence. X goes up, Y goes up, but it might not be X that's causing Y. Okay, we might think that it's X causing Y. It might be Y causing X. Okay, or it might be some other thing. This example is actually taken from the prologue, I believe, for Freakonomics, where they talk about this. And so I've stolen it shamelessly, but here's the example. There's a positive correlation between election spending and election results. Okay, that's not surprising. So you might suggest that the more money you spend, the more likely you're going to win an election. Okay, but then they suggest that people are not likely to get campaign contributions unless they're likely to win. Right? Because you're not likely to donate to somebody who's going to lose, right? That seems like a waste of money. Okay, so what causes what? Maybe there's a third thing going on. Okay, so they're very careful. They try to be very careful, especially in the social sciences where there are a lot of survey data where humans are involved, filling out the data. They're very careful, and they have to, in order to prove causation, you have to show there's a temporal relationship. This is really key. Okay, so there's some sort of temporal relationship that X actually happened before Y, and often this is the difficulty in a lot of these studies and a lot of these conclusions. If you have that, the rest of it has to do with making an experiment, and oftentimes you hear about medical experiments where they're trying to test a new drug, and so they need to show that a change in that variable, people taking the drug or not taking the drug, for example, would be a change, or dosage level actually produces a change in Y. Okay, so some group will randomly get no dose, some people will randomly get some dose, and they will make sure that other factors are not in play. Okay, this is known as a controlled experiment. And it's usually very time-consuming and very costly to perform one of these things. The medical profession especially is criticized for how slow drugs come out, right? There's some life-saving miracle treatment that somebody says, oh yeah, I found the cure for whatever. Why don't you use it? Well, because people's lives are at stake. Okay? So if you happen to be wrong, somebody dies. If you happen to be right, maybe not performing the experiment, somebody also dies. Okay, which is another school of thought, but that's not a dominant school of thought. People usually proceed with more caution. So these things end up costing a lot of time, and they're very slow and expensive. Anyway, correlation, not the same thing as causation, okay? But it might lead you to, hypothesize that there is causation and create an experiment. Okay, well, enough of that aside. Back to math. There's also conditional expectation. I mentioned this when we were... I think I got a little ahead of myself in one of the examples one day, but anyway, conditional expectation works like you think it does. It basically conditions the probability for the probability density function, okay, based on some event. Okay, so the definition is, for a random variable x, you can condition on some event a, and you write it the same way as you would normally write conditional probability. So the expectation of variable x given a, or if a, and it's the same weighted probability thing, but you take the probabilities based on the condition a. Okay, so the probability function is going to change. It's going to be conditioned on a, and that's it. Okay, so let's do an example of this just to make sure that we're all together. Okay, so suppose 2 standard dice are rolled. What's the expectation if it's known the result is at least 9? Okay, so the expectation if we didn't have that extra information of at least 9 is 7. Okay, but we know that the number, it can be either 9, 10, 11, or 12. Okay, so those are the only possibilities now. Okay, so let A be the event. The sum is at least 9. Okay, so we have 4 possibilities, and the probabilities of each of these are, well, there's 436, 336, 236, and 136. Okay, so those are the only, things, the only outcomes that are left, and they come in a ratio of 4 to 3 to 2 to 1. Okay, so that's one way of thinking about it, is that we're going to reweight this expectation to the probabilities, in a ratio of 4 to 3 to 2 to 1, like 4/10, 3/10, 2/10, and 1/10, right? Because there's 10 possibilities. Okay, another way is to not think about it and just use the formula, and that's perfectly fine too. Okay, so the probability of A is 10 over 36, and we can condition on each of those by, dividing by 10 over 36 in each case. That's what I'm going to do. okay, to be pedantic about it. But if you want to take the shortcut and say, well, the probability of 9 given that A has occurred is 4/10, you can do that too. And you'll see the 4/10 occur here. Okay, so let's do it. Okay, so we apply this formula. Okay, so the first possibility is 9. All the other ones have a probability of 0 given A, so we're not going to include those. So it's 9. And the probability of getting 9 given, probability 9 given A is the probability of 9, which is 4/36, divided by the probability of A, which is 10/36. Okay, and we'll do that for each. So 10 times, okay, so the probability of getting a 10 is 3/36, and divided by the probability of getting 9 or more, which is 10/36, okay, and so on. Okay, I'll give you a moment to catch up on the writing. Okay, big red's coming out. Okay, and you can see that, like, by 36, like, they're just, they're ripe for the picking. Right? Yeah, or you can, again, take the shortcut, but you're now in a probability space that is in a ratio of 4 to 3 to 2 to 1, and you could have said 4/10, 3/10, 2/10, and 1/10. Okay, shortcut works. Anyway, 9 times 4 is 36, 3 times 10 is 30, 22 and 12. So 30 plus 88 plus 12 is 100, divided by 10 is exactly 10. Okay, so the average roll, if you know that the result is 9 or more, okay, on 2 dice, is 10, which might be surprising, actually, okay, but also cool. Okay, questions about this? Okay, we have one important thing to prove today. That's the law of total expectation. Okay, so if you have expectations under a hypothesis, you have a collection, or partition the space, right? You can take the expectation if case 1 and then multiply by its probability, and take the expectation if case 2 and multiply by its probability, and so forth for all the cases. And it's basically taking a weighted average of weighted averages. And intuitively, this makes sense because this is what you've done forever when you calculate your grades, right? Okay, anyway, proof, because it's good for us. Okay, expectation of x. Expectation of x, start off with the definition. And then we're going to use this. Okay, so we're going to sub this in. Okay, for what are we going to use this for? Sorry, we're not going to use this. We're going to use this at the very end. Pardon me. Yeah, sorry, we're going to compress this down later because all right, come back to that in a second. First thing we're going to do is break this up into its constituent parts based on this hypothesis, and that's by using the law of total probability. Okay, so x times, and then we have let's see, the sum from I equals 1 to k of each of these cases. Okay, so it's going to be the probability that x equals x given hypothesis bi times the probability of bi. Okay, so we would like to use this at some point. Okay, and this is not too bad. You see, x times the probability that x equals x given a, x equals x given bi. We're just missing this x. That's okay. Okay, this sum doesn't depend on x, so we can sort of expand, sort of move that thing inside. Okay, that's getting closer. All right, sorry, I'm fussing with the paper. We just want to keep our goal in mind here. Anyway, we'll move the x inside. Okay, so that looks pretty good. Now, except the sum isn't right. the sum needs to be over x in range x, and it's got, well, that's no problem, because it doesn't matter what order we sum things in, right? So we can swap these two things and it won't affect anything. Okay, well, that's pretty good. You know, that's sort of what we want, right? So this bit here is looking really good. It's only that they have this extra bit over here. It's easy to deal with this extra bit, and I'm running out of room, so I'm not going to write two steps, but I think you can handle it. This bit doesn't depend on x, so we can common factor it out. We can move it here, and then we will have the thing that we need left. Okay, so that's going to be expectation of x given bi. Okay, so the two steps combined here, the sum from I equals 1 to k, the probability of bi, so we move that out. And then this bit here is exactly the definition as it is above, expectation of x given bi. Good? Yep. Okay, so let's do an example. I mean, the example is, you could have followed your intuition. By the way, a lot of you followed your intuition on question 2 of the test, okay, which is good, right? So you did law of total probability. What's the chances that Joe successfully crowns, right? So you sort of take all 3 strands and you average them, and you weighted them according to which possibility Joe opted for, right? Okay, here we have 2 strands, okay? So average height of people in the world, and just to make it more interesting, we're taking probably a better, more real statistic, that there are fewer males than females in the world overall. Okay, so 48.3% of people in the world are male, the rest female. The expected height of a randomly chosen male is 5'11", female 5'5". What's the expected height of a randomly chosen person? Okay, so if we sort of look at the, the statistics here, okay, so if, say, F is the event that they're female, the probability of female is 51.7%. Okay, the variable H goes according to 2 things, right? Not the probability. This is expected value, right? Okay, so there's no probability on it. It's density function. We don't know what the function is, actually. And we don't have to know what the function is. Okay, it could be binomial, it could be Gaussian, it could be anything. We don't actually have to know what the function is to do this problem. All we have is the expected height of not female is 5'11", right? Or 5 and 11/12 if you want it in terms of feet. And this would be expectation of height given female is 5 and 5/12, right? Okay, so you don't have to know what the random variable behaves like. You don't have any idea. You don't need to know, right? Okay, you just take a weighted average, which is really nice. Okay, so let H be the height. And let F be the event they are female. Okay, and then we use law of total expectation. Okay, so the expected height is the weighted average of the expected height if female. Okay, multiplied, so it's weighted by the probability that they're female, plus the expected height if they're not female, times the probability that they're not female. Right? And that makes sense, right? You're weighting by the 51% and 48 point. It's roughly 50-50. Okay, so we sort of expect something halfway in between 5'11" and 5'5", right? Which would be, 5'8"? Maybe we expect to get something that's, the males are pulling less than half the weight in this equation. So we probably expect something that's going to be a little less than 5'8", right? Okay, that's our intuition. I'm just thinking about, we can use a calculator though, right? Okay, so height of female, let's just do this. So 65/12 times, 51.7% plus 71/12 times 48.3%. And if you ran this through a calculator and then put it back into terms we can understand, this is 5 feet, 7.9 inches. Okay, which sort of gels with intuition, right? Roughly 50-50, it should be roughly 50-50 average. Okay, but slightly less because there are more females than males. Yeah. Okay. Any questions? We feel okay? Okay. We'll do the summary slide, and then we'll call it a day. Okay. Okay. So a lot of things have been done. We still have more to do. All right. These things don't have the variance of the various distributions we've done so far, which I think is Bernoulli and uniform. Those are the only ones we've done. We're going to do the other three. Okay, so that's on deck next. Okay, but that's for another summary slide. Okay, so this is just the mechanics of computing variance and covariance and all that stuff, and the law of total expectation. Okay, so first thing, the variance is the square distance from the mean. We take the expectation of that. This is a nice shorthand thing that you should use whenever you can. Covariance indicates how x and y sort of push each other. Okay, so x increases, y will also increase, so a positive covariance, or if it's negative, it will go down. It's defined to be this. It's sort of like the residual from that variance, like that total variance equation. Okay, so you go down to here, you see it occur, right? If x and y are independent, that thing is zero. It goes away. Okay, as you see in this next line. Anyway, properties of variance. If you you do a x plus b, you do something linear. The b goes away, and you get a squared. If you add two distributions together, you get this variance plus the covariance, 2 times the covariance. But these things go away if they're independent. And we have our law of total expectation, where you take a whole bunch of cases, a weighted average of weighted averages. Just go back for 1 second. This proof, covariance sort of came out of this proof. If you were to think of like the variance of x plus y plus z, right? How does this thing scale, right? You would do something similar. You would sort of say, well, it's x plus y plus z all squared minus expectation of x plus y plus z squared, right? And then you would do the same sort of calculation. But if you know how x plus y plus z all squared operates, this will end up giving us cross terms that look like this. Okay, all of them, except there will be all the pairs, right? So you'll end up with the variance of x and the variance of y and the variance of z, and you'll have the covariance of x and y, and you'll end up having the covariance of, sorry, I keep on writing covariance of x and z, and the covariance of y and z. Okay, so all the pairs will be represented in those cross terms, right? Okay, so when you expand those things out, and if it happens that they're pairwise independent, so x, y, and z are pairwise independent, all those things go away. Okay, so these things vanish,